Right, so I'm going to show you a little bit of magic. What we're going to do is we're going to kind of break the RSA method. Okay, so what should happen with RSA is that Alice encrypts and then maybe gives it to Bob, and then he encrypts. And what should happen is that Bob should then decrypt, and then Alice will decrypt, and we end up with a message. It can't work the other way around, or can it? So what we're going to do in this trick is we're going to get Alice to encrypt, Bob to encrypt, and then in any order, and it can be, we can get many people to encrypt, and we can randomize the order which they decrypt. We'll be able to decrypt in any sequence. Okay, so we'll have a look at how that is actually done. Okay, so I'll give you a quick background in RSA first. We pick two prime numbers. We select, we calculate the modulus, which is the multiplication of the two numbers. That's the thing that keeps the whole thing secure. If we can crack that, then we've compromised RSA. Then we calculate phi, which is p minus 1 and q minus 1. If it's 3 and 11, then we end up with 20. Then we select a value of our encryption key with no common factor with phi. So phi has factors of 2, 4, 5, 10, and so on. So let's select 3. Okay, so our encryption key is 3 and 33. We calculate our decryption key as d times e that we've done, mod, and that should be phi there. 20 equals 1. And then we get the result of our decryption key. Okay. Then we take for our encryption key, we take the message, raise it to the power of encryption key, take the mod of n, and then when we decipher, we take the cipher to the power of d and mod n, and we get the result back again. Okay. So here's the trick. So Eve invites Bob and Alice up onto the stage to show them the trick. Okay, so Eve asked Bob and Alice to select each of them a prime number each, and then said, go ahead and now calculate your encryption keys. So Bob selects 11 and Alice selects 5. We're just using small numbers to make it easy for us to see how the calculation, how the trick is done. And they determine n, which is obviously 55, and phi, which is 10 times 4, which is 40. So Bob goes ahead and realizes that the factors of 40 are 2, 4, 5, 10, and so on. So he selects 7, okay, and he's going to compute his d value, and he's got to make sure that d times the 7 mod 40 is equal to 1. And if you want, here's the calculation. Okay, so the value is 23 that allows that to work. Okay, so now he has his decryption key, 23, and so Alice will do the same. She selects 11, and they're sharing the same n. That's really important in this case. So she calculates that she needs a value of 11. Don't worry that the encryption and decryption keys are the same. It just happens that it happens in this case. Okay, so there we have. So Bob's encryption key is 755, decryption key 2355, Alice's key 1155, and okay, our decryption key is 1155. It just happens that it works out like that, but it's just as likely as any other number. So Eve says to Bob to go ahead and encrypt the message. Okay, so he does that, and then he gets he takes the message of 12, and he gets 23. And then she asks him to pass it to Alice. Alice then does a bit of a calculation. Eve waves her wand over it, and then at the end, Alice announces that the value is 12. Okay, so in this case, we've kind of broken RSA. It shouldn't really work like this. So how did it actually work? Well, basically, there's our keys. If we're using the same value of n, then it works out that when Alice takes a message to the power of a, our encryption key, and then Bob encrypts the value that's sent to the power of his encryption key, then we get a to the power of b, which is actually ab. It's a bit like Diffie-Hellman actually, and it only works because we're using the same value of n there for that. So it doesn't matter which way we decrypt. each of them will it will work no matter if we encrypt 10 times and have a random order of the decryption.